Okay, so I'm out on my front porch making this video for y'all today because I want to make sure that you understand what you read yesterday. So if you will look at the top of your electrons and atoms guided notes that you colored your little rainbow colors on, and you have the true false on the top, that's what I'm going to be working off of for the first part of class, and then we will talk about the Wacky Wave worksheet that you got yesterday as well. So our essential question basically was saying, what is the difference, which went in the first blank, between the frequency, the wavelength, and the energy of an electromagnetic wave of light? The order of these three words are not crucial to your existence. Just as long as you have those three words in those middle three blanks, you're going to be just fine. Take a minute if you haven't already, and they wanted you to answer those true-false statements on the top of your paper before you read. So before I go any further, take a second and make sure that you've answered those true-false questions, because we'll come back to that in just a minute. So go down to the bottom half of your page where you should see a picture that looks very similar to this. This is called the electromagnetic spectrum. It's a spectrum or an array or a visual representation of all the different types of waves that are flying around through the air out there. And so if you will take a look with me down over here on the left-hand side, you see things like radio waves, TV waves, microwaves, some kind of millimeter waves, which I'm not real familiar with in telemetry, and some infrared rays. This is like night vision goggles and cool stuff like that. It's also like when you go down to the cafeteria and you get a chicken sandwich and it's nice and warm. I promise it's not because they just cooked it. It's because it's sitting under a heat lamp. A heat lamp is also a form of infrared technology. Something else I find a little bit interesting, all the way down here on the left, we have sonar. Anybody ever heard of that? Sonar is the way that we make a map of the ocean floor without actually having to dive all the way down there, because the pressure's so great you would get crushed in a submarine. And so if we can't go down to the ocean floor, we can send waves from this machine, from a boat, down through the water, and it bounces back off the ocean floor. And we have computers that have made maps of the bottom of the ocean so we can see where the volcanoes are and where the cracks are and the different depths and all the different changes that are happening on the ocean floor with sonar waves. So take a look at the information that's below here. Look what it says about AM radio waves. One wavelength is about 3 football fields long. That's pretty crazy. Here we're talking about TV and radio waves being about 3 meters to 10 feet long. Here we're talking about wavelengths that are maybe only about 3 centimeters or about 1 inch long. So what's happening to my wavelength as I go this way? You should notice that the wavelength is getting shorter. So that means over here on the left-hand side, you should have figured out that this little upside down Y looking thing stands for wavelength. It's called a lambda. But you've got one of these in a box on the side of your electromagnetic spectrum, so label it with me. We are going to say that the wavelength on the left-hand side is long, which is the same thing as saying these guys have a high wavelength. Long means high wavelength. The wavelength, if you remember from reading yesterday, is from one part of the wave to the same part of the next wave. So this would be the wavelength of this wave if we were measuring. So what does that mean? So as we were going across and we hit this visible light spectrum, now the wavelengths are measured in nanometers. Nanometers are too small for me to even show you. They're so tiny. And then look what's on the right side of visible light. We've got ultraviolet, which is like the radiation coming from the sun. We've got X-rays. We've got gamma rays. These are all forms of radiation that we just talked about in nuclear chemistry that are really dangerous to your body and to your skin. Look what their waves look like in this wave picture. They're real scrunched up, close together, and again, they're measured in nanometers. Look at this one. This one's only about 30 times bigger than a hydrogen atom. So I'm talking picometers when we get down here. Can't even show you how small that really is in real life because they are so tiny. So over here on the right side of your picture in your box where it says wavelength, tell me about the distance between these two waves down here. It's really, really short, or what we would call low wavelengths. So, the wavelength is the distance between two common points on a wave. Then it asks you about the frequency of a wave. The frequency is down at the bottom of this box. You should have read yesterday that the frequency of a wave is how many waves per second pass by you in that 1 second. So in a split second, how many waves did we see? Or should we have seen if they were actually visible to our eyeball? Okay, so think about it over here. If you're sitting here and a second goes by and this wavelength is 3 football fields long, are you gonna see very many waves pass by in a second? And the answer is no. So down here where it says, what's the frequency of this wave? How often does this wave occur? You're gonna say that the frequency is low, which means it's not very exciting. Oh, I saw a wave, but there's not going to be one that comes around for a while. Okay, these are like the lazy side of the electromagnetic spectrum. They don't get in a hurry. Whereas if you looked at the frequency over here on this side, in a split second, how many waves went by? Holy moly, way too many for me to count. There were so many waves and they just came flying at me. I couldn't even count them all. Okay, that's what's happening on the right side of the wave. So on the right side of the wave, we would say that the frequency is very high. There are lots of waves per second passing by your eyeballs or your ears or wherever you're standing. And so think about this. If we're looking at this wave and we're looking at this long wavelength, low frequency wave, what type of energy would you suppose that that wave might have? Well, hopefully it makes a lot of common sense to say that if my wavelengths are long and it's not happening very often and it's not very exciting, the left-hand side has low energy. So fill that in next to the E. These guys are not very energetic. Football fields long. Now when we fly to the other side of the wave down here, those gamma rays that'll vaporize you when the nuclear blast comes and hits you in the face. Talk about the amount of energy with those guys. Those guys have a crazy high amount of energy. Crazy high. So high that they'll burn you to a crisp right when they touch you. Okay? So all of this is related to what we learned in the last unit with radiation. All right. So we've labeled our letters inside. Make sure that you colored, yours is down below, but there was a triangle that was up here above. Basically what they wanted you to do is shade this side red and shade the middle green and shade the other part blue with all the rainbow colors in between. Okay, if we're looking at this visible light spectrum, if you look at the R is closer to the long, low, and slow and boring side of this electromagnetic spectrum. R stands for red. If you look at the V side, which stands for violet, violet is closer to the high energy, short wavelength, high frequency side. So when you're looking at a rainbow on a rainy day outside, when you see red in the rainbow, I want you to think, oh, red doesn't have near as much energy as that violet or blue side. That violet or blue side has their waves much more scrunched together. So when we see light, we see white light coming from the sun, coming from a light bulb, but white light really isn't white. White light really is a combination of all of the Roy G. Biv colors, red, orange, yellow, blue, indigo, violet, oh, I forgot green. All of those colors, when they blend together, somehow make white. Pretty interesting, pretty weird. If you mixed all those colors together for paint, you would get black. But when you mix the light together, you see white. So in order to see what's underneath that white light, we have to use something called a prism. You might have used those in middle school, but that prism will break apart that light into its colors. The raindrops on a cloudy day or on a rainy day act like a prism, and so when the sunlight goes through the raindrops, it bends the light, and we call it refraction. When the light bends and it breaks apart into its colors, that is called refraction. And you see all of these different colors in a pretty rainbow. So, what do we want you to get out of this? We want you to know that the red side of light has low energy, low frequency, and long wavelengths. We want you to know that the violet side, high energy, short little wavelengths, high frequency. If I was a wave, I would live over here. Some of you calm and chill and quiet people, you would live over here. I can't ever calm down my brain. This is what my brain is like all day long. Okay, so hopefully you've analyzed this little spectrum. You should be able to relate now. Question 1 on the bottom of the page. How does emitted light relate to the electrons in an atom? So talk about those two relationships that I just talked about with you with the red and violet. And number 2 says, what is electromagnetic radiation? It's just waves that are emitted in different wavelengths, and we have this huge variety of waves that fit into this category. It's just all the different forms of waves that we have on the earth. So here it is in a little prettier format, so if you didn't quite get those relationships, there they are for you. I'll post this on my website later today while I'm at home with my sick kiddo, if you want to go back and look at this evening. So if you look at page 2 of your notes, page 2, I might draw a little wave. Just one is fine. You don't have to draw 5 waves for A, B, C, D, and E, but those are some really good vocabulary words that you really need to know the definitions of, the symbols for. We're going to talk about these things quite a lot in the next few days. So when you're looking at a wave, letter A says, describe the characteristics of a wave. Describe what is meant by wavelength. It is exactly like it sounds. It is the length of a wave. Be sure to include his symbol because, again, we're going to do that a lot. So the wavelength of a wave is really important to us. It is the length between the top of a wave and the top of the wave. Or we could measure it from bottom to bottom, That could be the wavelength. Or we could even measure from, we call this resting position to resting position. I had to skip this point because if I were to draw a line right here, this is not a complete wave. We only went through half of a wave. So a complete wave is an entire bottom and an entire top. That is an entire wavelength. And so this whole middle section would be considered my wavelength. The whole middle section. The frequency is kind of impossible to label on a wave without knowing how many waves passed by me at this second. So the frequency, the definition of frequency that I would write down for letter B is the number of waves per second. And the symbol is a cursive, kind of like a cursive F. Let me draw it again. That is the frequency, and it's the number of waves per second. And he not only has a little curvy F, but also write down he is measured in hertz. Sounds like a rental car company, which is Hz. Hz is how we measure frequency. You might have heard this before, maybe with radio speakers, maybe with radio stations. If you listen to 106.1, you're listening to 106.1 megahertz. That's the frequency of that radio station, 106.1 megahertz. And so that is how many millions of waves are passing by your ear every second. So that's B. If we look at C, the crest, the top of the wave is called the crest. So if you drew a picture, label the top of your wave as a crest. There's a town in Colorado called Crested Butte because it's the top of the mountain. So the top of the wave is also called the crest. Then we're going to label the bottom of a wave down here. I always say pigs eat out of the bottom of a trough. You put food in the bottom of a trough and the farm animals eat it. So the top of the wave is the crest. The bottom of the wave is the trough. The amplitude is just how high your wave is. And to be honest, that does not affect us very much in our class. When you get to physics next year, they do talk about the intensity of a wave as it relates to volume for sound and other things as well. But for us, it's not that crucial that you understand amplitude other than it's the height of the wave. So we've done part 3. We've labeled our waves. And so we're going to go through and talk about part 4. This is a really big idea, this relationship between frequency and wavelength, and sometimes it's hard for kids to understand. Anytime we put questions on a test about what happens if this one increases, does the other one increase, decrease, remains the same, blah, blah, blah. And so it gets really tricky. So we want you to really understand the relationship so you're not sitting there trying to memorize or guess on the test. So if you take a look at my 2 waves right here, they have a lot in common and they have some pretty big differences. The height of both waves is kind of sort of similar. Maybe the bottom one is a little bit taller, has a higher amplitude. But if you'll check it out, the top wave is labeled that it has 4 wavelengths in this 1 second. So we are measuring time from here to here. In that 1 second, 1, 2, 3, 4 complete waves have passed by me. So when 4 waves per second pass by, we say that wave has a frequency of 4 hertz. In this bottom wave, however, I only had 2 waves pass by me in that 1 second. So he has a frequency of 2 hertz. So logic should tell you that this guy at the top has a high frequency. And so if this guy has a high frequency, this guy at the bottom has a low frequency. Now let's analyze their wavelengths. So when their frequency is low, what kind of wavelength did this guy have from crest to crest? Well, if we're comparing it to the top wave, this top wave had a wavelength from crest to crest. That's pretty short. So when the frequency is high, the wavelength is short. At the bottom, when the frequency is low, the wavelength is long. I just remember my L's. So, what this means in math is that they are inversely related. If you look at question 4, it says, what does it mean when we say that wavelength and frequency are inversely related? So here's another way to look at this mathematically. I'm going to do it over here on the right side. When the frequency goes up, the wavelength goes down. Do you see this right here? I would put this in your notes somewhere. When the frequency goes up, the wavelength goes down. Now what happened in the bottom wave, the frequency went down, so the wavelength got longer and went up. So I would write that in your notes. So what do you notice about the sets of arrows? I'm hoping that you notice that they are opposite. And so in your notes, somewhere next to the word inverse, write the word opposite. So frequency and wavelength have an opposite relationship. When one goes up, the other goes down. Using your wave on the front side of your notes, you should be able to fill in the blanks for both of those relationships in your notes. When the wavelength is blank, the frequency is blank. We just did that one together. The second one, you have to think a little bit more. When the wavelength is blank, the energy is blank. So what happens to the energy when the wavelength is long? Which wave has more energy, the top or the bottom? Hopefully you realize which wave looks like Miss Dooley. And that's probably going to be this top wave. And so because of that, we're going to say this wave has high energy. And this bottom wave has low energy. You might also notice all of these start with the letter L. Low frequency, long wavelength, low energy. And all my highs and shorts go together. So number 5 says, what does it mean to say that frequency and energy are directly related? So let's take a relationship. So if you look at this relationship, check it out. Looks very similar to what we just looked at. We just changed the waves you were looking at to colors of the visible light spectrum. So now we're in that little triangle portion that you colored earlier with your red on one side and your green in the middle and your blue on this side. So we're taking a look at our red wave. And remember what we said, the red was closer to the long wavelength, low frequency side, so he had lower energy. And the blue had shorter wavelengths and higher frequencies, so he would be considered to have higher energy. Again, here's my wave, all crazy. Okay, so you've got to relate all of these 3 variables together. Take a look what it says down here at the bottom. Frequency and energy are directly related. What does that mean? Check it out. When the frequency is low, the energy is low. When the frequency is high, the energy is high. And so that's what they're wanting you to understand in number 5. The word direct means same direction. So in number 5, where it says directly related, write same direction somewhere. You might also want to put when the frequency goes up, the energy also goes up. So those arrows are going in the same direction for frequency and energy. So you've got a set of variables that are inversely related when we talk about frequency and wavelength. And then you've got another set of variables that are directly related. So now can you see what I'm talking about when I say that test gets tricky with who goes up, who goes down, who stays the same? So really understand these relationships. So we already colored that all in. Check this out. This is how many nanometers wide the wavelength is for red light. 750 nanometers is his wavelength. Look at violet light. His is only 380 nanometers. So his wave is a lot more scrunched together and looks like this. Red's is a lot longer and lazier and looks like this. So that's all we're trying to show you with this picture. Had a power glitch a minute ago. Have to start this slide over. It shouldn't affect you guys, but here we go. In your notes, you have a big box down at the bottom on the back page that says speed of light formula. I'm definitely going to need you to write down this formula right here. C is equal to, this is called a lambda times frequency. Some of you don't like that big times in the middle, so you could write it like you would in algebra. C is equal to lambda F. Same thing, just pointing out that it's not a plus sign. So then it asks you, what do all of these little letters mean that are new to us? The C stands for speed of light. So everyone needs to write down speed of light. Speed of light is 3.0 times 10 to the 8th meters per second. You don't need to write this part down because we don't want to write all those zeros. So 3 times 10 to the 8th meters per second. That's 186,000 miles every second. So if I had a light particle in my hand and I let it go and it traveled at the speed of light, in 1 second it could travel 186,000 miles. That's crazy fast. So the other thing I want you to notice about speed of light is that it's measured in meters per second. I'm always going to give you this number. It's not a secret. It never changes. It's a constant. So if I'm giving it to you and I'm giving it to you in meters per second, check out our second variable. This is called a lambda. Okay, you guys are going to call it a Y. I get it. But it's really called a lambda. So here's wavelength. So wavelength has to be measured in meters. And the reason wavelength has to be measured in meters is so it matches the speed of light. Here's the bad news. If I give you kilometers, can't use it. Centimeters, can't use it. Nanometers, can't use it. You're going to have to convert first into meters so it matches the speed of light. Don't write this down, just check this out. If I gave you 737 nanometers, we would have to put nanometers on the bottom. We would have to look at our gold foldable about the good man, King Henry, died Monday by drinking chocolate milk under Nana's porch, and find out that nano is 9 spaces away from meters, which is base. Meters is bigger, so he gets the 1. Nano is 9 steps away, he gets the 9. Nanos cancels out. Now you've got meters, which would be 7.37 times 10 to the negative 7th meters. Don't worry, I'll do other examples slower. Just wanted you to see if I give you something other than meters, you're going to have to do one quick train track, change it, then my meters match my speed of light. And so I can proceed with my problem. The last The last variable in our formula is the F, and we've already talked about that that is your frequency. We've also talked about that's your number of waves per second. We've also talked about that that is hertz, but another way you might see this written is 1 over S. So add that to your notes somewhere, and when we do an example problem, I'll show you what it means. Basically, what it means is hertz is the same thing as per second. So when I'm comparing this to the speed of light equation, hertz is comparing or looking at that S. So those two guys are going to be able to cancel out. A hertz is a per second. And notice that it's on the bottom in the denominator. That is what a hertz is. It's a wave happening every second. So now we've got our formula. Let's rock and roll. I love math. I'm going to make you a rock star. Hey, don't tune out. I know it's about to get hard. Watch my steps and you'll totally get this. So look at my steps that I have right here. See these 4 steps? Write this over in the left-hand margin. This is what I want you to do every single time we do a math problem. All right? It's because of the numbers that you're about to see that we want you to do it in this order and that we did that wave pre-assignment. So number 1 says, hey, write your formula. No one in this class is dumb as a rock. Everyone on every single question on the back of Wacky Waves can write the formula. So we're going to add another formula in this unit, but for right now, you only know 1. So we're going to write the formula. C is equal to lambda times frequency. And so hopefully you've written down those 4 things out in the margin. You're always going to write your formula every single time. Then, just like we practiced on the wave equation, we want you to rearrange the letters. Solve for the variable. Well, that requires me to actually read the problem. So here we go. Example 1 says a wavelength of light has a frequency of 4.51 times 10 to the 16th hertz. Whew, crazy number. That I'm going to label as my frequency. So underline that number and label that as your F. And let's see what it's asking us for. Calculate the wavelength. So we're going to put the little lambda Y symbol next to wavelength. So I want the wavelength. So that's what I'm going to put in the box. Remember, the box can't move. So who is next to the box that I have to remove? The frequency. And if you remember, we do that by dividing both sides by F. So we have rearranged the letters. My high school algebra teacher, I really took it in 8th grade, would have made us then rearrange this, and I'm going to do it just because it looks prettier. Wavelength is equal to C over F. So I've rearranged my letters. Now it's all pretty. I am ready for step 3, which is the easy part. We just did the hard part. Coming up with my new letters. Plug in your numbers and solve. So we have to look in our notes and find out what is C. C is always the speed of light. 3 times 10 to the 8th meters per second. Don't forget the letters. Don't just write down numbers, lazy butts. Divide that by the frequency. Well, I don't know the frequency. Oh, wait. Yes, I do. They gave it to me up here. They said the frequency is 4.51 times 10 to the 16th. So that's going to go down here. 4.51 times 10 to the 16th hertz. You know my favorite part is to cancel. Here I go. Nothing cancels. But, yes, it really does. Hertz and per second are the same thing. So I can cancel S and HZ. Now I'm only left with meters. And if you think about it, we're looking for wavelength. Can I measure the length of a wave in meters? Sure. So that's pretty much my clue that I'm doing this right. So now we're going to plug this into our calculator. And we find out that it's 6.65 times 10 to the negative 9th meters. Let's have a quick little sig fig discussion. A lot of you want to look at that 3 and say, it only has 1. You are totally right. Here's the problem. That is considered a constant, and we can't ever use constants for sig figs. So here's the general rule. Go back up into the problem that I gave you. Count sig figs up here. 4.51. Since this guy has 3, this guy needed 3. Don't forget to look out on the edge of the calculator and find that E that is missing out there. You're definitely going to need that. Okay, so that is an example on how to rearrange, plug in, solve for the missing piece.